The Sun is the star at the center of the solar system. It is a nearly perfect sphere of hot plasma, with internal convective motion that generates a magnetic field via a dynamo process. It is by far the most important source of energy for life on Earth. Its diameter is about 1.39 million kilometers, or 109 times that of Earth, and its mass is about 330,000 times that of Earth. It accounts for about 99.86% of the total mass of the solar system. Roughly 3/4 of the Sun's mass consists of hydrogen. The rest is mostly helium, with much smaller quantities of heavier elements, including oxygen, carbon, neon, and iron. The Sun is a G-type main sequence star, based on its spectral class. As such, it is informally and not completely accurately referred to as a yellow dwarf. Its light is closer to white than yellow. It formed approximately 4.6 billion years ago from the gravitational collapse of matter within a region of a large molecular cloud. Most of this matter gathered in the center, whereas the rest flattened into an orbiting disk that became the solar system. The central mass became so hot and dense that it eventually initiated nuclear fusion in its core. It is thought that almost all stars form by this process. The Sun currently fuses about 600 million tons of hydrogen into helium every second, converting 4 million tons of matter into energy every second as a result. This energy, which can take between 10,000 and 170,000 years to escape from its core, is the source of the Sun's light and heat. When hydrogen fusion in its core has diminished to the point at which the Sun is no longer in hydrostatic equilibrium, its core will undergo a marked increase in density and temperature while its outer layers expand, eventually transforming the Sun into the red giant. It is calculated that the Sun will become sufficiently large to engulf the current orbits of Mercury and Venus, and render Earth uninhabitable, but not for about 5 billion years. After this, it will shed its outer layers and become a dense type of cooling star known as a white dwarf, and no longer produce energy by fusion, but still glow and give off heat from its previous fusion. The enormous effect of the Sun on Earth has been recognized since prehistoric times, and the Sun has been regarded by some cultures as a deity. The synodic rotation of Earth and its orbit around the Sun are the basis of solar calendars, one of which is the predominant calendar in use today. The English proper name Sun developed from Old English sun and may be related to south. Cognates to English sun appear in other Germanic languages, including Old Frisian sun, sun, Old Saxon sunna, Middle Dutch sun, Modern Dutch sun, Old High German sunna, Modern German sun, Old Norse sunna, and Gothic sunno. All Germanic terms for the sun stem from Proto-Germanic sunon. The Latin name for the sun, sol, is not commonly used in everyday English. Sol is also used by planetary astronomers to refer to the duration of a solar, itself a translation of the Greek. The Sun is a G-type main sequence star that comprises about 99.86% of the mass of the solar system. The Sun has an absolute magnitude of plus 4.83, estimated to be brighter than about 85% of the stars in the Milky Way, most of which are red dwarfs. The Sun is a population 1, or heavy element-rich, star. The formation of the Sun may have been triggered by shockwaves from one or more nearby supernovae. This is suggested by a high abundance of heavy elements in the solar system, such as gold and uranium, relative to the abundances of these elements in so-called population 2, heavy element poor stars. The heavy elements could most plausibly have been produced by endothermic nuclear reactions during a supernova, or by transmutation through neutron absorption within a massive second-generation star. The Sun is by far the brightest object in the Earth's sky, with an apparent magnitude of minus 26.74. This is about 13 billion times brighter than the next brightest star, Sirius, which has an apparent magnitude of minus 1.46. The mean distance of the Sun's center to Earth's center is approximately 1 astronomical unit, about 150 million kilometers, or 93 million miles, though the distance varies as Earth moves from perihelion in January to aphelion in July. At this average distance, light travels from the Sun's horizon to Earth's horizon in about 8 minutes and 19 seconds, while light from the closest points of the Sun and Earth takes about 2 seconds less. The energy of this sunlight supports almost all life on Earth by photosynthesis, and drives Earth's climate and weather. The Sun does not have a definite boundary, but its density decreases exponentially with increasing height above the photosphere. For the purpose of measurement, however, the Sun's radius is considered to be the distance from its center to the edge of the photosphere, the apparent visible surface of the Sun. By this measure, the Sun is a near-perfect sphere with an oblateness estimated at about 9 millionths, which means that its polar diameter differs from its equatorial diameter by only 6.2 miles. The tidal effect of the planets is weak and does not significantly affect the shape of the Sun. The Sun rotates faster at its equator than at its poles. This differential rotation is caused by convective motion due to heat transport, and the Coriolis force due to the Sun's rotation. In a frame of reference defined by the stars, the rotational period is approximately 25.6 days at the equator and 33.5 days at the poles. viewed from Earth as it orbits the Sun. The apparent rotational period of the Sun at its equator is about 28 days. The solar constant is the amount of power that the Sun deposits per unit area that is directly exposed to sunlight. The solar constant is equal to approximately 1,368 watts per square meter at a distance of 1 astronomical unit from the Sun, that is, on or near Earth. Sunlight on the surface of Earth is attenuated by Earth's atmosphere, so that less power arrives at the in clear conditions when the Sun is near the zenith. Sunlight at the top of Earth's atmosphere is composed by total energy of about 50% infrared light, 40% visible light, and 10% ultraviolet light. The atmosphere in particular filters out over 70% of solar ultraviolet, especially at the shorter wavelengths. Solar ultraviolet radiation ionizes Earth's dayside upper atmosphere, creating the electrically conducting ionosphere. The Sun's color is white, with a key color space index near 0.3 when viewed from space or when the Sun is high in the sky. When measuring all the photons emitted, the Sun is actually emitting more photons in the green portion of the spectrum than any other. When the Sun is low in the sky, atmospheric scattering renders the Sun yellow, red, orange, or magenta. Despite its typical whiteness, most people mentally picture the Sun as yellow. The reasons for this are the subject of debate. The Sun is a G2V star, with G2 indicating its surface temperature of approximately 5,778 K or 5,505 degrees Celsius, 9,941 degrees Fahrenheit, and V, that it, like most stars, is a main sequence star. The average luminance of the Sun is about 1.88 gigacandela per square meter, but as viewed through Earth's atmosphere, this is lowered to about 1.44 gigacandela per square meter. However, the luminance is not constant across the disk of the Sun. The Sun is composed primarily of the chemical elements hydrogen and helium. At this time in the Sun's life, they account for 74.9% and 23.8% of the mass of the Sun in the photosphere, respectively. All heavier elements, called metals in astronomy, account for less than 2% of the mass, with oxygen, roughly 1% of the Sun's mass, carbon, neon, and iron being the most abundant. The Sun's original chemical composition was inherited from the interstellar medium out of which it formed. Originally it would have contained about 71.1% hydrogen, 27.4% helium, and 1.5% heavier elements. The hydrogen and the most of the helium in the Sun would have been produced by Big Bang nucleosynthesis in the first 20 minutes of the universe, and the heavier elements were produced by previous generations of stars before the Sun was formed, and spread into the interstellar medium during the final stages of stellar life and by events such as supernovae. Since the Sun formed, the main fusion process has involved fusing hydrogen into helium. Over the past 4.6 billion years, the amount of helium and its location within the Sun has gradually changed. Within the core, the proportion of helium has increased from about 24% to about 60% due to fusion, and some of the helium and heavy elements have settled from the photosphere towards the center of the Sun because of gravity. The proportions of metals is unchanged. Heat is transferred outward from the Sun's core by radiation rather than by convection, so the fusion products are not lifted outward by heat. They remain in the core, and gradually an inner core of helium has begun to form that cannot be fused because presently the Sun's core is not hot or dense enough to fuse helium. In the current photosphere, the helium fraction is reduced, and the metallicity is only 84% of what it was in the protostellar phase, before nuclear fusion in the core started. In the future, helium will continue to accumulate in the core, and in about 5 billion years this gradual build-up will eventually cause the Sun to exit the main sequence and become a red giant. The chemical composition of the photosphere is normally considered representative of the composition of the primordial solar system. The solar heavy element abundances described above are typically measured both using spectroscopy of the Sun's photosphere and by measuring abundances in meteorites that have never been heated to melting temperatures. These meteorites are thought to retain the composition of the protostellar Sun and are thus not affected by settling of heavy elements. The two methods generally agree well. In the 1970s, much research focused on the abundances of iron group elements in the Sun. Although significant research was done, until 1978 it was difficult to determine the abundances of some iron group elements via spectrography because of their hyperfine structures. The first largely complete set of oscillator strengths of singly ionized iron group elements were made available in the 1960s, and these were subsequently improved. In 1978, the abundances of singly ionized elements of the iron group were derived. Various authors have considered the existence of a gradient in the isotropic compositions of solar and planetary noble gases, correlations between isolar wind-implanted noble gases. The core of the Sun extends from the center to about 25% of the solar radius. It has a density of up to 150 grams per cm cube, about 150 times the density of water, and a temperature of close to 15.7 million kelvins. By contrast, the Sun's surface temperature is approximately 5,800 kelvins. Recent analysis of SOHO mission data favors a faster rotation rate in the core than in the radiative zone above. Through most of the Sun's life, energy has been produced by nuclear fusion in the core region, through a series of nuclear reactions called the proton-proton chain. This process converts hydrogen into helium. Only 0.8% of the energy generated in the Sun comes from another sequence of fusion reactions called the CNO cycle, though this proportion is expected to increase as the Sun becomes older. The core is the only region in the Sun that produces an appreciable amount of thermal energy. Through fusion, 99% of the power is generated within 24% of the Sun's radius, and by 30% of the radius, fusion has stopped nearly entirely. The remainder of the Sun is heated by this energy as it is transferred outwards through many successive layers, finally to the solar photosphere, where it escapes into space through radiation or advection. The fusion rate in the core is in a self-correcting equilibrium. A slightly higher rate of fusion would cause the core to heat up more and expand slightly against the weight of the outer layers, reducing the density and hence the fusion rate and correcting the perturbation, and a slightly lower rate would cause the core to cool and shrink slightly, increasing the density and increasing the fusion rate and again reverting it to its present rate. From the core out to about 0.7 solar radii, thermal radiation is the primary means of energy transfer. The temperature drops from approximately 7 million to 2 million kelvins with increasing distance from the core. This temperature gradient is less than the value of the adiabatic collapse rate and hence cannot drive convection, which explains why the transfer of energy through this zone is by radiation instead of thermal convection. Ions of hydrogen and helium emit photons, which travel only a brief distance before being reabsorbed by other ions. The density drops 100-fold from 0.25 solar radii to the 0.7 radii, the top of the radiative zone. The radiative zone and the convective zone are separated by a transition layer, the tachocline. This is a region where the sharp regime change between the uniform rotation of the radiative zone and the differential rotation of the convection zone results in a large shear between the two, a condition where successive horizontal layers slide past one another. Presently, it is hypothesized that a magnetic dynamo within this layer generates the Sun's magnetic field. The Sun's convection zone extends from 0.7 solar radii to near the surface. In this layer, the solar plasma is not dense enough or hot enough to transfer the heat energy of the interior outward via radiation. Instead, the density of the plasma is low enough to allow convective currents to develop and move the Sun's energy outward towards its surface. Material heated at the tachocline picks up heat and expands, thereby reducing its density and allowing it to rise. As a result, An orderly motion of the mass develops into thermal cells that carry the majority of the heat outward to the Sun's photosphere above. Once the material diffusively and radiatively cools just beneath the photospheric surface, its density increases, and it sinks to the base of the convection zone, where it again picks up heat from the top of the radiative zone, and the convective cycle continues. At the photosphere, the temperature has dropped to 5,700 K, and the density to only about 1/6,000 the density of air at sea level. The thermal columns of the convection zone form an imprint on the surface of the Sun, giving it a granular appearance called the solar granulation. At the smallest scale and supergranulation at larger scales. Turbulent convection in this outer part of the solar interior sustains a small-scale dynamo action over the near-surface volume of the Sun. The Sun's thermal columns are Bénard cells and take the shape of hexagonal prisms. The visible surface of the Sun, the photosphere, is the layer below which the Sun becomes opaque to visible light. Photons produced in this layer escape the Sun through the transparent solar atmosphere above it, and become solar radiation, sunlight. The change in opacity is due to the decreasing amount of ions, which absorb visible light easily. Conversely, the visible light we see is produced as electrons react with hydrogen atoms to produce ions. The photosphere is tens to hundreds of kilometers thick, and is slightly less opaque than air on Earth. Because the upper part of the photosphere is cooler than the lower part, an image of the Sun appears brighter in the center than on the edge or limb of the solar disk, in a phenomenon known as limb darkening. The spectrum of sunlight has approximately the spectrum of a black body radiating at 5,777 K, interspersed with atomic absorption lines from the tenuous layers above the photosphere. The photosphere has a particle density of about 0.37% of the particle number per volume of Earth's atmosphere at sea level. The photosphere is not fully ionized. The extent of ionization is about 3%, leaving almost all of the hydrogen in atomic form. During early studies of the optical spectrum of the photosphere, some absorption lines were found that did not correspond to any chemical elements then known on Earth. In 1868, Norman Lockyer hypothesized that these absorption lines were caused by a new element that he dubbed helium, after the Greek sun god Helios. 25 years later, helium was isolated on Earth. During a total solar eclipse, when the disk of the Sun is covered by that of the Moon, parts of the Sun's surrounding atmosphere can be seen. It is composed of 4 distinct parts: the chromosphere, the transition region, the corona, and the heliosphere. The coolest layer of the Sun is a temperature minimum region extending to about 500 kilometers above the photosphere. and has a temperature of about 4,100 K. This part of the Sun is cool enough to allow the existence of simple molecules such as carbon monoxide and water, which can be detected via their absorption spectra. The chromosphere, transition region, and corona are much hotter than the surface of the Sun. The reason is not well understood, but evidence suggests that alpha waves may have enough energy to heat the corona. Above the temperature minimum layer is a layer about 2,000 kilometers thick, dominated by a spectrum of emission and absorption lines. It is called the chromosphere, from the Greek root chroma, meaning color, because the chromosphere is visible as a colored flash at the beginning and end of total solar eclipses. The temperature of the chromosphere increases gradually with altitude, ranging up to around 20,000 K near the top. In the upper part of the chromosphere, helium becomes partially ionized. Above the chromosphere, in a thin about 200 kilometers transition region, the temperature rises rapidly from around 20,000 K in the upper chromosphere to coronal temperatures closer to 1 million K. The temperature increase is facilitated by the full ionization of helium in the transition region, which significantly reduces radiative cooling of the plasma. The transition region does not occur at a well-defined altitude. Rather, it forms a kind of nimbus around chromospheric features such as spicules and filaments, and is in constant, chaotic motion. The transition region is not easily visible from Earth's surface, but is readily observable from space by instruments sensitive to the extreme ultraviolet portion of the spectrum. The corona is the next layer of the Sun. The average temperature of the corona and solar wind is about 1 million to 2 million K. However, in the hottest regions it is 8 million to 20 million K. Although no complete theory yet exists to account for the temperature of the corona, at least some of its heat is known to be from magnetic reconnection. The corona is the extended atmosphere of the Sun, which has a volume much larger than the volume enclosed by the Sun's photosphere. A flow of plasma outward from the Sun into interplanetary space is the solar wind. The heliosphere, the tenuous outermost atmosphere of the Sun, is filled with the solar wind plasma. This outermost layer of the Sun is defined to begin at the distance where the flow of the solar wind becomes superalfvénic, that is, where the flow becomes faster than the speed of alpha waves, at approximately 20 solar radii. Turbulence and dynamic forces in the heliosphere cannot affect the shape of the solar corona within, because the information can only travel at the speed of alpha waves. The solar wind travels outward continuously through the heliosphere, forming the solar magnetic field into a spiral shape, until it impacts the heliopause more than 50 astronomical units from the Sun. In December 2004, the Voyager 1 probe passed through a shock front that is thought to be part of the heliopause. In late 2012, Voyager 1 recorded a marked increase in cosmic ray collisions and a sharp drop in lower energy particles from the solar wind, which suggested that the probe had passed through the heliopause and entered the interstellar medium.